Are you hearing me well? Yes, I am hearing me. So, no, first of all, I want to advertise again for those of you who didn't hear about it. FOCM conference it will be in, so that's actually that is the FOCM Society website. So that's the way I go to the FOCM conference website this year. So I'm glad to see there is a very big part of the FOCM crowd here, and Mike was one of the founders of the society. So if you go to the website of the conference, it will take place in Montevideo in December 11 to 20, and it's really a nice conference. For those of you who know, many people here are going to speak there. There are like 3 or 4 workshops that are really linked to this program. So one is the computational algebraic geometry workshop, which is organized by Agnes and by Carlos Andrea and by Greg Smith, thank you. Another one is the real number complexity workshop organized by Felipe and by Shogata and Carlos Beltran. And there is another one on continuous optimization. I think that Cynthia is speaking there, and there are many workshops related to the people here. So maybe when you see the list of participants, those of you who haven't registered yet want to go. So look, that's a former student of mine, Santiago Laplagne, made this, and this is extraordinary. So you have all the participants by day, get tempted and go to FOCM. And then we also have all the abstracts of talks and posters up to date. So for instance, if you go there, you will see the abstracts of the plenary talks. The conference is starting with Andres Emeredi. He's giving the first talk, and Mike is giving the second talk in the first day. So for instance, if you click here, you have all the abstracts, and you can see. Okay, so this is the advertisement of the conference. Please come. So now, I'm going to start my talk. Good. Thank you very much. First, yes, thank you. Okay. First, I'd like to thank the organizers for having me speaking here. It's a great pleasure. And I will speak on a subject which might be a little bit farther than the ones we heard about on these days, except it's a little bit related. The second part of the talk will be a little bit related with Naresh's talk, because it will treat about things on finite fields, polynomials on finite fields. But I will start with the Nullstellensatz. So let me remind what the Nullstellensatz is about. Hilbert Nullstellensatz, that's the German word for the theorem of the place of zeros. That's Hilbert, more or less in 1883, and in its weak form, what it says is that if you have polynomials f1, fs in a polynomial ring over a field, and for a moment let's assume that the field is algebraically closed, and if these polynomials do not share any root in the algebraic, so if these polynomials do not share any root, so the variety they define is empty, this is exactly the same than saying then you can write 1 as a polynomial combination of f1, fs. That is what the Nullstellensatz says. So written in an ideal way, it would say this. But if we write the coefficients, it would say that there exist polynomials g1 with gs in k of x1, xn, such that you can write 1 as g1 f1 plus gs fs. So this is a very important theorem in algebraic geometry. And what we can observe first is that it translates a geometrical problem, the problem of having or no solutions, to an algebraic question of writing 1 as a polynomial combination of some given polynomials. But as it is not constructive. So if you do not do if you do not know anything else, you cannot really solve the problem in this way. But even if it's not constructive in this way, what it says is if there are some polynomials J1, Gs, then if they exist, they will have some degree. So you can, knowing that they will have some degree that exists, and let's call the degree, the degrees of the Fi's in all my talk will be di, and they'll always be bounded by a d. And let's assume that if this gi exists, they have a certain degree bounded by capital D. Which means that if you have a capital D, you can state every polynomial gi as a polynomial of degree d in the x1, xn variables with unknown coefficients. And then when you write these expressions, what you observe is that you will marry the coefficients, unknown coefficients of the gi's with the known coefficients of the fi's. And so that will give you for each monomial in this expression, that will give you a linear form with unknown coefficients of gi's, known coefficients of fi's. So you will end up solving this problem, solving a linear system of equations, comparing the exponent by exponent. So the only exponent which is not, the only coefficient which is not 0 here is the constant coefficient. So what does that mean? First observation, that means that if you start with polynomials, for instance, with coefficients, with rational coefficients in Q, and you solve your linear system of equations, you will never leave the rational field Q. Solving linear systems of equations, you do not leave the field, which means that here we do not need to assume that K is algebraically closed, but what we are looking for are solutions in the algebraic closure of K. But these polynomials G1, Gs will have coefficients in the base field K. Okay? Moreover, same reasoning, if you start with a domain A with quotient field K, and if you start with polynomials F1, Fs in A, so you will end up with polynomials G1, Gs in K of x1, x1, xn. But these polynomials G1, Gs will have a common denominator. And this common denominator will be a non-zero number in A. So which means that you will end up having polynomials in A and an alpha in A minus 0, such that alpha can be written as a polynomial. Oh, thank you. Yeah. Very kind. Such that alpha can be written as a polynomial combination of F1, Fs. So now everything is in A of x1, xn. The Fi's, the Gi's, and this alpha is a non-zero number in A. So, okay. So we decided that only observing that this means to solve a linear system of equations means that now we have a domain and we have things in the quotient field of the domain. And another thing is that now, imagine what is people speak about effective Nullstellensatz. What is effective Nullstellensatz? It is given polynomials F1, Fs with certain degrees, give an a priori bound for the polynomials Gi's, degree bound for the polynomials Gi, so find such a D, which will realize this Bezout identity. That is usually called a Bezout identity. So which realizes this Bezout identity. So why is that? Because once you have your D, imagine that you have your D, and you want to solve this question as a linear system of equations, what do you have? You write that. How many unknowns do you have? The unknowns are the number of coefficients of all polynomials Gi's. So you have S polynomials Gi's, and each polynomial is of degree big D, capital D, in n variables. And as was explained yesterday in the first talk, the number of coefficients of a polynomial of degree d in n variables is this combinatorial number. So this is more or less something like s d to the n, let's say, of this order. That's a number of unknowns. And the number of equations corresponds to the number of coefficients you have in this expression. So this expression has degree d plus capital D, n variables, and in n variables. That is a number of coefficients you will have to look for. And this is more or less something like d, small d plus big D to the n. So that is the size of the linear system of equations you will have to solve. So why do I say this? Because I said effective Nullstellensatz is bounding the degree. What is arithmetic Nullstellensatz? That's the subject of my talk today. Arithmetic Nullstellensatz is if you start with a domain with a notion of height, for instance, if you start with a equal the integer numbers, you can imagine that a height of a polynomial is the log of the max of the absolute value of the coefficients. That's the height of a polynomial. So height of a polynomial f in z of x1, xn is the log of the max of the coefficients. So that is an example of a domain with a height notion. So height of a number is the log of the number. Why is it that? Because it's the number of bits you need to write the number in a computer, essentially. And another example of a domain is this is A equals Z. Take A equal a function field, function ring, sorry, in any numbers of variables you want. So that's why I put T with a bar. Any number of variables you want. So that's, and here in this case, the notion of height is simply of a polynomial f in k of t of x1, xn is simply the degree in t of the polynomial f. So that will be the notion of height of a polynomial in this case. So this is in the case f in k of t of x1, xn. And this is the case f in z of x1, xn. Okay, these are the two notions of two domains I will work with, and the two notions of heights I will use. And I am introducing height for what? Imagine that you started with G1, F1, Fs in A of x1, xn with the notion of height. You may wonder too, is okay, if I have a Bezout identity, what is the bound for the degrees, effective Nullstellensatz, and what is the bound for the heights? What is the bound for this alpha, which is an integer number or a polynomial in k of t, and what is the bound for the height of this polynomial? So that is arithmetic Nullstellensatz. Okay, is effective plus the height bound. Clear? The problem is clear. Yeah. So first observation. So first observation, once you have a degree bound, you immediately inherit a height bound. Why is that? Because you have this linear system of equations that you can solve. So if you use Cramer's rule, you have this big matrix that you need to solve, and this matrix, the coefficients of this matrix will be the coefficients of the polynomials Fi's. So imagine they all have height h, small h, because it's a log.
See down there, Teresa, maybe I want to put this for it.
Yeah, there was one reason why I didn't want to.
Oh, it is clear on the screen. So. Well, you probably are trying to avoid in the center because you're going to pull the center apart. But if you'd written first in the center, then you could
That I was trying to do that and I forgot when I started. But, yeah, that's, no, it's so.
Are you good?
I can go here. So here is your big matrix that you have to solve. Here are your unknowns. Here is your 0, 0, 1 or 0, 0, 1. So you use Cramer's rule. The size here of everything is h. The height of every polynomial is h, coefficients. So what do you have at the end? No, it's big H. Let me not take logarithm yet. Take really the degree of the polynomials or the coefficients of the f. So at the end, what will you have here? Essentially, you will have h to the d. When you take by Cramer's rule, you take the determinant of this, and the denominator is also the determinant here. So the size will be h to the d. If you take the log, that will be d.
It's not h to d, but the size of this matrix.
Yeah, and what is the size of the matrix?
You wrote it down.
D plus n choose n.
Thank you. Yeah, because if not, it would be very simple. You're right, thank you. So it's h to the s d to, let's say d to the n to simplify, like this. So if you take the log of this, d to the n log h. So if you started with polynomials whose coefficients have height log of h, then you end up with this. So what happens? The first general bounds for this problem were given by Grete Hermann in 1923, and what she found is a bound of type d equals small d, degrees of the fi's, to the 2 to the n, more or less, essentially. So a bound which is doubly exponential in the number of variables. So this was Grete Hermann, but then there is this example which appeared, and which is the worst example that anyone could ever find. Now I would like
No, that's fine. I was going to suggest, if you wanted to, when you wanted to project your equations, they could go on the sideboard, so you could just right here. She doesn't have to, you're going to project a slide or two.
I need to keep the example I'm writing before the slide.
No, what I mean is she could put the slide up there, and then you can just write wherever you want.
Okay.
Would you prefer that? If so, she'll do it.
Okay, thank you.
All right.
So let me give you an example. The example is a very famous example, is due to Braunabel, Philippon, Masser, a lot of people in the 80s, 86 more or less. And it's a very nice example. So it's a system of n polynomials in n variables. Very simple. f1 is equal to x1 to the d. f2 equals x1 xn to the d minus 1 minus x2 to the d. fn minus 1 equals xn minus 2 xn to the d minus 1 minus xn minus 1 to the d. And then the last polynomial, and this example I will give it in the parametric case. So it's a polynomial with coefficients in k of t, minus xn minus 1 xn to the d minus 1. So if you look at these polynomials, these are n polynomials in n variables. The variables are the x. This is it's in k of t, and it has degree, every polynomial has degree exactly d. And it's very easy to see that these polynomials do not share any common root in the algebraic closure of k of t. No, because if x1 is equal to 0, then x2 needs to be equal to 0, and you go on and you go on, and you have that xn minus 1 is equal to 0, and then you have that t to the h is equal to 0. But we're in the coefficient there. So which means that there are no common zeros, so I will be able to write a polynomial alpha in t as a polynomial expression of f1, fn, which means that alpha is equal to this, and this is a very common trick. What one does is I will specialize this identity in values that make every polynomial vanish from the last one backwards to the second one, because I cannot make all the polynomials vanish, of course. So what do? I choose xn to be 1 over a variable, u. So if xn is 1 over y, let's say. And then I fill it, I choose xn minus 1 in such a way that this vanishes. So the right choice is, since I won't be able to do it now, everybody can verify this. If you take xn minus 1 to be t to the h, y to the d minus 1, this dies. And then I replace xn minus 1 by this value, xn by this value, and who is xn minus 2? And I will write it for you. T to the dh, y to the d square minus, no, I did one, yeah, d square minus 1. And we continue like that, backwards. And then at the end, x1 is t to the d to the n minus 2 times h, y to the d to the n minus 1 minus 1. And this is what I called y. Underline y, thank you. So what happens now when I replace in this expression, I specialize this expression in this underline y. So everything dies except the first one. So at the end, we will have this alpha, which is a polynomial in t, which be equal to g1, which depends on t and x, times f1 specialized here. But f1 specialized here is simply the first coordinate to the d. So this gives t to the d to the n minus 1 times h, y to the d to the n minus d. Very interesting. No? And this is, of course, this is an expression which depends on t and h. It's all polynomial except for this term. So if one looks at this very violently, one says, okay, something in t needs to be this, and here I have this y to the dn minus d. How can I get that? And the only way you can get that is that the degree in xn of this gy has to be very big. This is good for every value of y. It has to be very big. It has to kill this part. So this means that if you look at this, the degree in xn of g1 has to be greater than dn minus d. And also, if you replace y by 1, this means that this t to the if you replace y by 1, everything is polynomial. There is no more rational expression here. And this means that the degree of alpha as a polynomial in t has to be greater than dn minus 1 times h. So this is the conclusion. So let me summarize this in...
I missed that. Why is the degree in alpha d?
So put here y equals 1. So if you put y equals 1, this is an expression in t, a polynomial in t. Polynomial in t times polynomial in t, that needs to be a polynomial in t. So this degree divides this degree. Or divides, it's less or... This polynomial divides this polynomial. So the degree... Okay? So I will summarize this as the max of the degree of G1 F1, remembering that the degree of G of F1 is D, this gives this, and the height of alpha is greater than D n minus 1 times H. So this is a lower bound for the problem. If we want a general solution, we will get at least these bounds. We are looking for upper bounds, we will get at least these bounds. Is it clear what I'm saying? So this is when I want to show the example. Something happened? Nothing. Ah, because this.
Your computer sleeps.
Yeah. So how do I?
Make you wake your computer up.
Well, okay, we skip I will skip it because. So what I wanted to show is that there is effectively an example which realizes the Bezout identity with exactly this. No, this is because my computer is very slow and it's a disaster.
You work.
Okay, I work. So what do, okay. So about first, effective Nullstellensatz. So about effective Nullstellensatz, there is a big gap between this double exponential bound by Grete Hermann and the known lower bound. So there were a lot of people working on that, and there were a lot of work in the 86, 87. So a series of papers, and the best bound was on 87 by Collard, and it was of type d to the n, modulo some detail. But then, in 2005, Jelonek came out with a very beautiful geometric proof of the same fact, where he improves Collard's bound. So,
If you log into your computer to show how.
thank you. This is.
I mean, I didn't know what to do, but.
Is it here too? Yeah.
It's on the side. If you want to put it in the center here, she'll project it. Open it up. She'll project it to the
Okay.
center for us. I'll turn this on. Oops.
Okay. No. Let's use that.
It's warming up.
No, this multimedia thing is not. Okay, I will show it here. Look, this is the solution. Can everybody see here, or kind of strange? But here are my polynomials, the one I gave at the beginning. And if you look here, this is the expression t to the d n minus 1 times h equals a polynomial combination. And if, for instance, here is the last polynomial is hidden here inside. The fn is hidden here. The fn was t to the h minus xn minus 1 xn to the d minus 1 is hidden here. And then the fn minus 1 is hidden here. The f2 is hidden here, and f1 is hidden here. So here you have a polynomial combination, and if you look, every term cancels. The only term that survives is this one, which is equals to this. So this is exactly a Bezout identity with the stated bounds that were written here and now disappeared. Here. With the exact bounds. So what I want, turn out.
She'll get
You'll do that. You'll do that. Okay. So.
Unplug the laptop now.
Okay, I won't show I have a second slide, but I don't do it. I don't show it because this will be terrible. This will be, I'm sorry. I'm sorry for this. Well, this will be terrible. So anyway, I told you that if you have a degree bound, you have a height bound. But our degree, the best degree, is d to the n. So this would give a height bound of type d to the, no, where is my height bound?
Right there.
Here. Okay. So this would be a bound of type d n square log h. So that is what Cramer's rule gives as a height bound using the best degree bound. And this is the lower bound people know. So if you can compare, there is really a gap between the exponent n minus 1 here and the n squared here. There is an exponential gap. So arithmetic Nullstellensatz dealt with putting bounds for the heights. So there was also a lot of work on that. The first working on that was Philippon, who gave a bound for the denominator for the height of alpha only in the case E equals Z. So Philippon and then also Iger and Berenstein, this way, Berenstein-Iger. And I would like to report here on a result with Carlos Andrea and Martín Sombra. Which is the following one. I'll treat the cases E equals Z and E equal K of T, the parametric case, and the A was the domain there, okay? So you start with polynomials f1, fs on A of x1, xn, which do not share any common root in the algebraic closure of the quotient field of these domains. So you end up with an alpha in A minus 0 and of G1, GS in A of x1, xn, such that, so this result is for S bounded by n plus 1 polynomials. It's an exact result for S for less than n plus 1 polynomials. The result is that the degrees in X of G, Y, Fi are bounded by the products of the polynomials, and the height of alpha, which in the case K of T means the degree in T of alpha, and in the case Z means the log of the absolute value of alpha, and the height of the GIs plus the heights of the Fi are bounded by an expression which is very precise. It depends exactly on the degree of each polynomial and on the height of each polynomial. Here is for J different from L. So it's a sum of this type. And this is the bound in the case K of T. And in the case Z, there is a correction term which is of type O of n log n times the products of the degrees. So this is the result we got in this situation. And I would like to, so I will make a couple of comments on this result. But first I would like to look again at our example that we had here.
Excuse me, Teresa. Alpha
Yes.
J, where was it defined? Alpha sub J. Or is it, oh, this is D. I'm
H.
sorry, I'm sleeping. This is D sub J. Sorry, it's the product.
D sub J, H sub L. So that is the height of each of the polynomials. Okay? So let's look at this example in this case. So in this example, we have n polynomials. We're in the good situation, n polynomials. And all the polynomials have degree D. But look at the heights. The only polynomial which has a height, which is not 0, is this one, which has height h. So which means that in this expression, there is only one term which survives. It's the term when you chose L equal n, so you get d to the n minus 1 times h. So this is the height bound you obtain when applying this result to this set of polynomials. And the degree bound, of course, is the product of the degrees, which is what we got there. So in this case, it's an exact match. So this bound matches exactly the lower bound in this case. Not in the integer case. In the integer case, we have this correction term. The reason why there is a big difference, no, not a big difference, this difference between the two cases is mostly because when you look at the height of a polynomial, in the parametric case, the height of a product is the sum of the heights. But when you look in the integer case, if you take two polynomials with coefficients in z and you take the product, the height of the product is not the sum of the heights. There is a term, because you have to add a lot of terms. There is a correction term. So the fact that you have to add this lot of terms is the fact that gives you this correction term here. So that's the difference between the two cases. And I don't know if that will be solved at some point. Another interesting example that I will give before switching to the second part is the example of the resultant of polynomials. So we can obtain the same result, but instead of working with one group of variables, we can work with several groups of variables and get precise results for each group of variables. So imagine you have polynomials f0 to fn plus 1, to fn, excuse me, generic polynomials of degree di's. Generic meaning that you take unknown coefficients, variable coefficients. So t alpha x to the alpha in n variables. T0 alpha, t n alpha, x to the alpha, and here of degree dn, this one of degree d0. So, and you take the resultant of this. So the resultant of this family of polynomials is, as you know, a polynomial in the coefficients which belongs to the ideal, so which can be written as a polynomial combination. And it's known that the degree in each group of variables ti of the resultant is the product of the other product for g different from I, dj. That is the degree in each group of variables of the resultant. So when you apply this result to this situation, you obtain exactly that. So really, the polynomial alpha you obtain applying this result is a scalar multiple of the resultant. So this bound is not tight for the x, but it is tight for the degrees in t's. So that is essentially the first part of the talk. But I would like to report on how this Nullstellensatz is being used as an ingredient in proofs for problems on finite fields. So somehow there is a switch between structures. And for this, what is used actually is not this Nullstellensatz, but the strong Nullstellensatz, which is, I think that everybody knows that, but if you have a f1, fs polynomials and an f which doesn't vanish on the common roots of f1, fs, so f doesn't vanish on the common. So what you know is that there is a alpha in A a power mu in n such that alpha f to the mu belongs to the ideal f1 fs. So if f doesn't belong to the what is the condition that I'm let me vanish on v of f1 fs.
That does vanish.
Does vanish.
And
You don't mean this.
right?
If it vanishes. If it vanishes on that, then you know you're lying in the ideal.
Yeah, yes, I'm confused. Does vanish, of course. Yeah, yeah. Excuse me. Yeah. So everybody knows that the strong Nullstellensatz is a consequence of the weak Nullstellensatz by the famous Rabinowitz trick, and a slight modification of this trick allows also to give bounds for this alpha, for this mu, and for these j's in these conditions. So actually, this is what is being used for the things I saw over finite fields, mostly a size for the denominator, and in the case z. So there are like three problems that I want to mention, and I will speak only on one of them. So the first one is from a paper by Bombieri, Bourgain, and Konyagin of 2009. And what I found interesting is the switch of structures, the fact that they can solve a problem on finite fields, switching to C, to the characteristic 0, but not to a rational program, to C. So this is about, I call it a witness theorem. But it is not a witness in the sense that we heard today. It's a witness in the sense of Smale. So I will explain it. So you fix n, you fix d, and then there exists a constant which depends on n and d, a small one, and two big constants which depends on n and d, such that for any prime p, prime number p, and any group, multiplicative group in the finite field fp multiplicative, at least one of the three following things happens. One of the three happens. Bourgain, Konyagin. One, P is small in some sense. The prime is small, which means P is bounded by the C2, which depends on ND. Second, the group is small. P is small, or the group is small, which means that it really has a small projection in one dimension. So the group has a small projection. There exists alpha different from beta exponents with alpha beta bounded by d. This will be exponents such that the projection in one dimension of the group, the size of the projection is bounded by the constant C1.
I'm confused. I'm sorry. You said for all P, and then you say P is small.
No. One of the three things happens for all P. Either P is small, or if P is big, we will have one of these conditions. So, let me write it. Projection in one variable. If you have a gamma here, which is a gamma 1, gamma n, you project to gamma to the alpha minus beta. That's gamma to the alpha divided by gamma to the beta, no?
G is contained in this to the end.
Yeah, so go up ahead, yeah.
To the n. Yeah, which order? Yeah.
Put the star up.
This one here. The other, okay. Thank you.
Well, we all know what you mean.
So either P is small, either the group is small, or either, that is the witness part, there exists a point in the group which is a witness for all polynomials of degree d and height and small height, which is a witness for all polynomials of small degree and witness for all polynomials of non-zero of degree bounded by d and height bounded by epsilon. Excuse me, p to the epsilon. And here by height I mean the absolute height, not the logarithmic height. What does that mean? That if I take any polynomial f in z of x1 x1 xn, which is non-zero, of degree bounded by d, and of height, absolute height, non-logarithmic height, bounded by p to this epsilon, then f in this gamma is different from 0. So there is a gamma in the group which is a witness for all polynomials of small degree and small height. That's the witness theorem in the sense of Smale. So, and what is interesting is, I'm not going to comment on the proof of this result. I'm going to comment 1 minute in the proof of the second result I want to mention. But in the case of one variable, it's a very simple idea. What they say is, if this doesn't happen, then it won't happen for a gamma and gamma square, for instance, gamma and gamma square, which means that there will be a polynomial for gamma, which vanishes on gamma, of small degree and height, and there will be a polynomial for gamma square, which vanishes on gamma square. So, if you have the polynomial f1, which vanishes on gamma, and f2, which vanishes on gamma square, the polynomial f1 and the polynomial f2 to the x square have a common root. So the resultant vanishes. Mod P, because you are mod P. The resultant vanishes, but which means that the resultant, when you look at it in Z, is divisible by P. So if the resultant is non-zero, this gives a bound for P, because it's bounded by the resultant. And if the resultant in Z is 0, for any choice of gamma and gamma square, then you will end up showing somehow that your polynomials are cyclotomic polynomials, and etc., etc., etc. But the reasoning is very neat. So they look at a polynomial which vanishes mod P, but they look at it in the integers. So the polynomial has two possibilities. It is 0, and if it's not 0, it's divisible by P. So that is how it works. So the second result, which is completely different. So, well, okay. But has the same. So, what I said about the resultant is the case of one variable. If you want to go to many variables, you use the strong Nullstellensatz. You find a polynomial which has to be in an ideal And you have here a number which is 0 mod p, and this gives the conclusions you're looking for. The second result is a result on size of product sets in FP. And this is Bourgain, Garayev, Konyagin, Sparlinsky, 2012. So what they say is, if you have S different from T in FP, and they look at the sets that I denote H, which is the set of ratios x plus S divided by x plus T for x between 1 and H. They look at this set. So this set has H elements, if one looks at it. And what they say is that there exists a universal constant C1 such that for all R in N, there exists a constant which depends on R only, satisfying that for all primes P and H such that there is this relation between H and P, so H is small enough compared to P, then the size of the products of R elements of A H, so you multiply R elements of this form, and you look how many elements you obtain at the end doing this multiplication. So if you were looking at the product, you would have H to the R elements. But here you multiply them and you can have repeated elements. So the size of this is philosophically what it should be, as big as it can be. So it's exponential of minus CR log H divided by log H times H to the R. So it's a multiple of the biggest possible size. And again, so this is also a result. It's completely different than this in its flavor. It's a result on finite fields, but what they do again is that they translate this result to a result in C. And how do they do that? They look at the map which sends an element X in the interval 1H. So they look at the interval 1H to the R, and they send it to the product X plus X1 plus S, X1 plus T, times XR plus S, XR plus T, X1, XR, here, and there. So they look at this map in FP. But then they look, okay, when do two images here will be the same? So if I look at two elements here that have the same images, that will give a polynomial relationship, because the numerator of the first one times the denominator of the second one has to be the numerator of the second one times the denominator of the first one. So this gives a polynomial relationship. So this polynomial relationship, I will create an ideal with all the possible polynomial relationship of that type, and I will translate this ideal, which is in fact over FP, I will look it in Z in the characteristic 0 case, and I will show that this ideal has something that is out of the diagonal in it. And so that is the way that they use to translate. It's always the same thing. They switch a problem on finite fields, they switch it to C. And in C, it's easier to solve. Complex algebraic geometry is easier than in the finite field case. So they go to C, they solve it in C, and then they come back. So, and there is a third example I'm not going to speak about. There is a third example which completely different flavor too, is finding points of high order in varieties over finite fields. So you have a curve on defined over a curve defined over a finite field, and you want to find how many points of high order it has. And also, again, there is switching to the C case, the complex case, using the strong Nullstellensatz at some point, creating an auxiliary polynomial which belongs to a variety, and then you have such an identity, but if this identity holds, since you have sizes for this alpha, you know that alpha cannot vanish if P is sufficiently big. If P doesn't divide alpha, this cannot vanish, so which means that this polynomial will vanish, and then blah blah, and the argument follows. So I will end here.
You mentioned at the very end, you mentioned the construction of auxiliary polynomials.
Yeah.
Are these another application, possibly Diophantine approximation, like Baker's theorem? Like in Baker's theorem, there's auxiliary polynomials. Would resultants, would these kind of Nullstellensatz help at all there?
I have no idea, but that would be interesting to look at this.
Okay. Because in Baker's theorem, you need lots of lines.
Yeah, actually, a last comment that I didn't say is I was speaking about two cases, Z and K of T. The results on Z, so there were previous results on Z. The results on K of T are new, but the reason why I mentioned this is because in all these results, they only work on prime fields with P a prime, because if you work in FP, even if you don't have any notion of size, you do have a notion of size. Elements in FP are bounded by P somehow. But if you work in the field FQ with Q P to the n, you doesn't have the analogous notion of size. So the analogous notion of size would be looking at the field FQ as a quotient field, no? Ft divided by a minimal polynomial. And then you can write your elements in FQ as polynomials of a certain degree in T, in a variable T. So in that sense, that's work that we are trying to do with some of these people. The Nullstellensatz, the parametric Nullstellensatz could be helpful for generalizing this kind of results to finite fields which are not FP, of the type FP. So that's
So in your result, the main result, you assume that the number of polynomials is at most n plus 1. How is it just a technical assumption? Because I would expect that if it's more polynomial, that everything is easier, right?
Actually, it's in the case of more than n plus 1 polynomials, you can reduce to n plus 1 polynomials. It's easy to reduce to that case, but you lose the exact dependency on each height and each degree, which is bad in some cases. And the reason is due to the proof, but it's a geometric proof. So in the proof of this Nullstellensatz, it's what Jelinek did, the Bezout identity comes from a coefficient of an implicit equation of a map. So the map will depend on the fact that you have less polynomials at the dimension of the ambient space, or n plus 1. So it's important in the proof, in this proof. So actually it's not easier if you have. There is no proof. All the results on the Nullstellensatz, there is a difference between the cases less than n polynomials and more than n polynomials.
Any other questions? Okay, well, let's thank Teresa again.